Good morning. Last lecture we looked at how to tackle various kinds of conditions other than loading in the analysis of statically indeterminate trusses. Okay. Today we are going to concentrate on the same thing for beams. Okay. And one of the points that additional points which I had forgotten to mention in my last lecture, I looked at support flexibility, lack of fit, thermal stresses. There is also the consideration of support settlement. Okay. So, in this particular lecture when I am looking at beams, I will also look at what affect support flexibility as well as support settlement. These are two different things. A member can be actually rigid and can displace rigidly. Okay, that is settlement. When does that happen? See, support flexibility is where we are considering the fact that a pier can deform axially. However, let us consider the situation of support settlement. When do we get the situation of support settlement? Well, the pier is actually rigid. In other words, so there is no deformation, it is actually rigid. The only problem is that the pier support, which is the foundation is not rigid. The foundation deforms under the load that the pier puts on the foundation and it settles. Okay. And if the foundation settles, then the top of the pier also settles, and if the top of the pier settles, then the support of the beam on top of the pier will also move, and that is support settlement. Okay. So, today we are going to be looking at beams, and this is the problem that we had looked at last time, which was a two span beam with a load in the center span of one of them, and we solved how to get the forces in all the members as well as all the supports. Okay. And that we did last time. So, this time I am going to look at first of support flexibility. What happens when I have a flexible support? So, let us take the situation that let me not consider both of them flexible, let me just consider one of them flexible. So, let me take that this continues to be a roller support, but this is flexible. Okay. And I have this load. Okay. And this is flexible with the spring constant K, which is equal to 1 upon F, the flexibility constant can be. Okay. So, this is the problem. Now, how would the problem change because of this flexibility? Let us see. The problem still remains the same. In other words, I can solve this problem by considering this as my base structure. So, I am removing this, plus this. Okay. So, now I have solved this problem, How is the entire thing going to be different? The difference is that, note that here we computed x1L, if you remember, this is the x1 due to load, then we computed x1x, remember that, and in the last case where this was this way, we took the compatibility condition is equal to x1L plus x1x is equal to 0. Okay. because in the real original structure, what was the displacement? 0. However, when you have a flexible foundation, what happens? Flexible support, what happens? Okay, this is no longer true. So what do you have? Let's see what happens. This is under this load. Okay, so this one and this one are identical to what we had computed for this case. There we had put it equal to 0 and computed the value of x1. Here in the actual structure, if I have a load x1 in the support, what is going to happen to the force in this member? Think about it. Okay, you will see that if there is a force x1 here, this spring is going to be subjected to compression. And if it is subjected to compression, then what happens actually? This member is going to compress. Now this point cannot go anywhere. So if the member compresses, what's going to happen? This point is going to come down. How much is it going to come down by? Well, that depends on what is the deformation in the member. How do we compute the deformation in the member? If you look at it, the member, the spring is subjected to a compressive force of x1, and if it is subjected to a compressive force of x1, then what is the deformation of this? The deformation of the spring is going to be equal to x1 by k, and minus. Why minus? Because if x1 is this way, the deflection is, the deformation is compression, and deformation is compression, then what happens to this point? This point actually goes down by the value of delta S. And so therefore, for this particular situation, once we have the flexible support, the equation becomes x1L plus x1x is equal to minus delta S. Why minus? Because x1 and x1L and x1S are taken as positive in this direction, and delta S, if you look at it, is actually downwards. Okay, so now the thing is, I'm going to put it as positive because I'm going to put delta S to be positive when the spring expands. When the spring expands, okay, the spring expands, it's positive. If the spring compresses, this is negative. So if you put that, delta S, if it was positive, this would also be in this direction. So it's going to happen that x1L plus x1S will be equal to plus delta S. Okay, so if I plug that in, and if I take the values that I got from the previous case, if you look at it, what was my x1L equal to? 625 upon EI. So this was x1L is equal to, let me put it on another sheet, x1L was equal to 625 by EI, x1x was equal to 2000 upon 3 EI into x1. Okay, and what is delta S equal to? Minus x1 upon k, and therefore by putting that into the compatibility condition, which is x1 plus x1x equal to delta S, what we get over here is equal that 625 upon EI plus 2000 upon 3 EI into x1 is equal to minus x1 upon k. Okay, and if you look at this, k is a known factor because it's a spring constant. We know the flexibility. Okay, so therefore we can find out x1 directly, because this will become nothing but 625 EI plus 2000 x1 plus x1 by k is equal to 0, and this you can solve for x1. Note that because of the foundation flexibility, the value of x1 changes. If you look at this, the value of x1 actually goes down due to the foundation flexibility. And that makes sense, because if you really look at it, what's happening here? You see, because if you really look at this, this one, if you look at the deformation pattern, what's going to happen? This is going to go like this and this. Okay? So in reality, because of the due to the loading, you're going to have a compression in the spring, but due to the deflection, you're going to have an extension in the spring, and therefore the compression in the spring is negated a little by the extension, and therefore the value of x1 goes down due to the foundation flexibility. Okay? So this is how you consider the effect of foundation flexibility. Note that in this particular case, as opposed to the truss, okay, the foundation flexibility directly has an effect on the internal forces in the member. The bending moment diagram will change because the support reaction has changed. Okay. Now let us look at the situation of foundation settlement. How does foundation settlement have an effect? Let's take the same case. So I have looked at foundation flexibility. Now we are looking at foundation settlement. Okay. How will foundation settlement come in? Well, let's look at this. Let's say that this foundation settles by a delta value. Okay? And we want to know what that effect is going to be equal to. Well, you see, how would I solve this problem? This would be equal to, again, you have to understand that the entire procedure is based on the same premise, plus okay. So now here, what are we getting? We are getting a fact that we find out x1L. Note that this x1L is going to be the same as before, so this is going to be 625 upon EI. We're going to find out x1S, and this again is going to be the same, so it's going to be 2000 upon 3 EI, because there is no effect over here. However, when you write the compatibility condition, what will it be? x1L plus x1S is equal to, now instead of 0, what is the displacement? Is this. And if you look at this, what is this? This is going to be minus delta, because remember, I'm taking upwards as positive, so this delta is actually a negative value, so it becomes negative delta. And if you really look at it, all that does is x1L plus x1S plus delta is equal to 0. And if you really look at it, this is going to be equal to, so this is going to be 625 EI plus 2003 x1 plus delta is equal to 0. And if you really look at it, the value of x1 goes up because of the support settlement. And that makes sense because due to the support settlement, this is going to take up a much larger value of reaction, because support settlement causes a larger reaction to come up. Okay. So you see, foundation flexibility and foundation settlement actually does not affect the problem, the solution of the statically determinate problems themselves. All that foundation flexibility and foundation settlement both do is that they affect directly the compatibility conditions that you have. Okay? So, whereas in the original case you would have x1L displacement due to load plus the displacement due to the redundant force x1 is equal to 0. Okay? When you have foundation flexibility, it is not equal to 0, it is equal to the displacement due to the flexibility of the foundation, and that is related to the force in the foundation itself. Okay? As well, and when you have foundation settlement, all you have is that the value of the foundation settlement comes in directly and you can compute it from there obviously. Okay? So, therefore, the only aspect of foundation flexibility and foundation settlement, or in support flexibility and support settlement, is that your compatibility conditions are affected. The analysis of the statically indeterminate are not affected. Okay. So much for foundation related matters. Now, let us look at the other kind of situation, where today, if you remember, I am always looking at other kinds of loads. Okay? So, in other words, the effect of what is known as non-load effects. Okay? Non-load effects. What are non-load effects? Foundation flexibility or support flexibility, foundation settlement or support settlement, thermal stresses, lack of fit. I have already talked about lack of fit in trusses, and I am not going to talk about lack of fit in beams, okay, because it involves a little bit of a difference. For example, a beam being longer does not really affect the stresses in the beam. Think about it. In this particular case, if this beam, instead of being 5 millimeters was 10 meters, was 10.1 meters, what would happen? The only thing that would happen is that these rollers would just move to the right and give no forces in the member. Okay? In other words, lack of fit does not normally have any effect on beams, because you see, lack of fit has an effect on axial forces. And remember that in beams, okay, axial forces are not of major consideration normally. Okay? So, that is why lack of fit is not a major issue as far as beams are concerned. So, that is why I am not considering that in right now. However, thermal stresses can have a large effect. Okay? The only difference is that again, uniform rise in temperature of the member gives rise to axial deformations. And again, the uniform rise in the member does not really have a tremendous effect on beams. It does have in such certain situations. We'll look at problems. You know, we've got the entire course where we're going to be solving a lot of problems. What I am trying to do in the beginning is try to lay the theory, so that later on we were going to be solving a lot of problems, and when we solve the problems, that is when you actually know that when even lack of fit or uniform rise in temperature could have an effect in beams and frame structures. Okay. However, there are certain situations where you cannot really say beam, frame, truss, it may be a combination. Okay. So, there are going to be various, but those I will leave for solution of example problems directly. Right now, we are looking at, in essence, the theory or how to consider the various effects. Later on we will see, by solving actual problems, how these have an effect in reality. Okay. So, let us now look at a situation where you have thermal stresses. Now, I just said that uniform temperature rise has no effect on beams, because again they are essentially lead to axial deformations, and axial deformations directly do not have a large role to play in beams, because beams essentially are subjected to flexure. Okay. So, what kind of thermal stresses would have an effect on beams? Let us look at that. Let me start off by looking at a simply supported beam. So, this is a statically determinate beam. So, statically determinate beam, what kind of thermal stresses would give rise to problems? Well, let us see. Let us have a situation where the top of the beam is heated. This can, when can this happen? Well, let us think of this as a room. Okay, let us think of this as a room. A room is typically colder than the outside. Okay, assuming Indian conditions, summer. Okay, if it was winter, then probably the outside temperature would be less than the inside temperature. Okay. However, the point that I am trying to make is that the delta T at the top and the delta T at the bottom are not equal to each other. In other words, the temperature differential exists. There is a thermal gradient across the beam. Thermal gradient. What does that mean? The temperature here and the temperature here are not the same. When there is a thermal gradient set up, what actually happens? Let's look at a particular face. What happens? Well, if you look at it, before the temperature went up, this was the face. Okay. Now, the temperature at the top goes up by delta T. So, what will happen? This point, note that this, I am looking at a cross section. Okay. So, this is the beam. What is going to happen to that beam? Okay. If you really look at it, this point, because it has been subjected to delta T, is going to go alpha delta top. This is going to be the strain at this point. And what is going to be the strain at this point? It is going to be alpha delta T bottom. Since these two are not the same, these two are not going to displace in the same. And as long as the temperature gradient is uniform, in other words, it is linear from the top to the bottom, you will see that each one will deform separately, and what you ultimately have is not only, if you look at the neutral axis has gone in this fashion, but if you look at the section, okay, it has actually rotated. Rotated means there is a flexure. If there is a flexure, what is going to happen? If you look at this, if delta T was higher than delta B, this is how the member would go, in flexure. The bottom would go in compression, the top in tension. Okay, if the inside temperature was higher than the outside temperature, then the member would deform in this fashion. Okay. The member would deform in this fashion. So therefore, a differential temperature actually leads to flexure in a simply supported beam. Okay. So not only does loading lead to flexure, differential temperatures also lead to flexure. And how much is that flexure? Let's look at that. Okay. Remember that this is equal to d theta. And if you look at this, if this is delta x, then this goes dx, dx. And d theta, if you look at it, is going to be equal to alpha delta t dx minus, because remember that d theta is positive in this direction, so that's why it becomes negative, alpha delta top dx all upon what? This, the depth of the beam, okay. So therefore, d theta by dx, what is that? The curvature. Curvature is given by alpha delta t bottom delta t upon d. This is the real curvature due to a differential temperature. And once you have the real curvature, then how do you find out anything? Well, this is the real curvature. What we did was that we also evolved that real curvature was m upon ei when you have loading. When you have loading, this is m, where this is the moment due to the loading, okay, and this is kappa due to that, and therefore virtual work gives us what? Virtual work gives us that m kappa dx. So whether that kappa is due to m upon ei or whether it is due to differential temperature, it makes not one bit of difference. This is the virtual moment established due to the virtual force system that we develop in the structure. So let me now go back to the problem that we were looking at originally, and let us take this situation. This is the structure, and I have a situation where the top delta T top is equal to minus 20 degrees and delta T bottom is plus 20 degrees. Let me put this kind of a situation. Why have I put this situation? Because if you look at this, what is the delta T at the neutral axis? You will see it's 0 degrees. In other words, this leads to, this temperature differential leads to pure flexure, because the neutral axis point, there is no strain in the neutral axis. Okay? That's why I am setting up a pure flexure kind of a situation. And there is no other load. And I have to find out the bending moment in this indeterminate truss due to this temperature differential. Okay? Let us see what happens. Did this have, this temperature differential, did it have any effect as far as forces were concerned? You will see that in a statically determinate, temperature only gives rise to flexure without giving rise to any forces. Okay? So there are no forces or bending moments in the structure. However, you will see that in a statically determinate situation, you do have this. And let us try to solve this problem. Let me put a few things in here. I am going to say that alpha is equal to 1.2 into 10 to the power of minus 5 millimeter per per degree centigrade. Note that strain per unit temperature. Okay, so that's alpha. Okay, so that's all I'm going to set up. Okay, so this is all that I need right now. Okay, and let us say that the beam depth of the beam is equal to 50 centimeters. So that's going to be 500 millimeter, which is equal to 0.5 meter. Okay, as long as you use units consistently, you will never have a problem in getting any solution. Okay, and then I'm still keeping the same thing. So this is 10 meters, 10 meters. Okay, so therefore the problem statement here is due to this differential temperature, where the top is minus 20 degrees and the bottom rises by 20 degrees. Okay, so there's a temperature differential of 40 degrees between the top and the bottom. What would be the forces in the supports and the bending moment diagram for this statically indeterminate truss? And I'm given that the depth is uniform, depth of the beam is uniform. So in other words, this is the beam where the beam is 50 centimeter deep. Okay, so this is my problem statement. How do I solve this problem? Again, we go back to the basic structure. This is my structure. Okay, and what I need to do is I need to find out how much this has gone up due to the differential temperature. If note that if this does not go up or down due to the differential temperature, you will not have any support reaction here, you will not have any x1, and then if you do not have any x1, the temperature will not have any effect on the structure. So therefore, we have to first see the situation that due to the temperature, is there a displacement here? That's my first, and then of course we add up this and put it equal to 0, and all those, find out this displacement x1, and the compatibility condition is x1 of t plus x1 of x equal to 0. So note that if this is equal to 0, this is equal to 0, and this is equal to 0, then x1 is equal to 0, and if x1 is equal to 0, there are no forces in the members and there is no effect of the temperature, differential temperature. So the whole thing hinges on whether there is an x1 of t due to the differential temperature, and that is our whole focus over here. Okay, so let us see what happens. Okay, now I've already done here that what is the effect on of the differential temperature. This is the curvature that happens due to differential temperature. Okay, so if I do put that, what is the, and note that the differential temperature is the same. In other words, all along the bottom you have plus 20 degrees, all along the top you have minus 20 degrees. Okay, so what is the curvature? The curvature, if you look at this, is uniform from here to here. And what is that curvature value equal to in this particular case? It's equal to alpha, which is 1.2 into 10 to the power of minus 5 divided by 0.5 meters. Okay, so that is alpha into delta t. So if you look at this, what is this? Delta t. Delta t bottom is plus 20 degrees minus delta t at top, so minus 20 degrees. Okay, so if you look at this, this is equal to 1.2 into 10 to the power of minus 5 into 40 upon 0.5. So if you put that together, you get 96 into 10 to the power of 5 radians per meter. You can see that the units of alpha are millimeter per degree centigrade, or millimeter per millimeter does not really have any units. We can say it per degree centigrade. Here we have 40 degrees centigrade, so that multiplies. So the top becomes nothing, no units. The bottom is in meters, so what we have is per meter is the, and what is kappa? Kappa is the rate of change of theta with length. Okay, so kappa is d theta by dx. What is theta given in terms of radians? And what is length given in terms of, in this particular case, meters? So it is radians per meters. 96 into 10 to the power of. This is uniform. In other words, if I were to draw the actual, in the real kappa, it would be uniform across the board and would be equal to 96 into 10 to the power of minus 5 radians per meter. Okay. Now, you see, I have to, so that's my, if I put A, B, C, A, B, C. Due to the temperature, I have a constant flexure across the entire beam of 96 into 10 to the power of minus 3 radians per meter. So does that give an effect? So I need to find out what does that lead to in terms of this. So what do I do? Well, again, using the principle of virtual work, okay, which is really to find out a displacement, I give a unit. Corresponding to the displacement, I give a unit virtual force, okay, and I find out the internal forces. If I look at the internal forces, what do I get? If you look at the curvature is also this way. Because the bottom increases, the bottom actually increases, and therefore you have a situation where the top compresses, the bottom increases, and the flexure is positive in this way. Okay. So this one is going to be 10 units. Okay. So this is my small m diagrams. Okay. And what I need to do is, I need to find out, to get x1 of t is going to be 1 into x1 of t. That's the work done. External virtual work is equal to this, and the internal virtual work is going to be over from A to C, okay, small m into kappa dx. Remember, this m upon EI, m upon EI is nothing but the real, so this is the virtual moment, this is the real flexural deformation, and this integrated over the entire length. And so if I put that, this is going to be equal to, what's the moment? Again, integral area of the moment. If you look at this particular one, the area would be equal to 10 into 10 into half into 2 multiplied by kappa, which is this value. So 96 into 10 to the power of minus 5. So what happens here? It becomes x of t turns out to be equal to, this 10 plus 10 is 100, you get 96 into 10 to the power of minus 3 meters, which is equal to 96 millimeters. Note that x1 of t turns out to be 96 millimeter, which is not a very small displacement. So you see, because of the temperature differential of 40 millimeter, x1 of t is equal to 96 millimeter. Now how do I find out the forces? Well, I have to find out x1. Okay, I found out, note that I have found out x1 of t, I need to find out x1 of x. I have already found out x1 of x earlier. Remember? What was the x1 of x? X1 of x is this. This does not change. Okay. So, if I put that in, if I plug that in here, what do I get? I get x1 of t plus x1 of x equal to 0. x1 of t is 96 into 10 to the power of 5 meters, and this is 2000 upon 3 EI into x1, okay, is equal to 0, and from that you can find out the value of x1. Once you find out the value of x1, it's a statically determinate structure, and if it's a statically determinate structure, you can find out the bending moment diagram. I am not going into that detail, because actually you need to put in the value of EI, etc., to actually solve for it. Okay. So, in a sense, I am just coming down to the fact that how to compute the effects of thermal stresses on beams. Okay. Now, you may say, well, you have not considered any loading, but you see, again I go back to the same point that I made earlier, that if I have a temperature as well as a loading, how would I do both of them together? I would consider only the loading, then I would only consider only the temperature, find out all the effects, add the two up, totally add it up, algebraic addition, and then I have the effect of all the things together. Okay. So, I boil down to the entire fact that you have a situation where you can find out temperature, thermal stresses in beams. Note that exactly in the same way you can consider frames too. Remember last time, well, 2 lectures ago, I talked to you about how beams and frames really, in terms of new thought processes, there are no new thought processes, because the only difference between a beam and a frame is geometry. A beam lies along one direction, a frame lies in a plane. Okay? That is the only difference between all these. So, now what I would like to do today is, I have developed the theory for the following things: the force method, okay. I have looked at the force method, I have applied the force method to both trusses and beams, and the thought process is the same. Trusses, axial, main load transfer, beams and frames, flexure, main load transfer. This is the essential difference between the two. So, we have looked at how to consider the force method for trusses as well as beams and frames. And what are the kind of things that we have looked at? Pure loading, external loading, which is the most common situation. Our analysis is normally always for external loading. However, we over the last 2 lectures have looked at a variety of other effects. We have looked at foundation, flexibility. Again, I use the word support and foundation together. Then we have looked at support, foundation, settlement. We have looked at lack of fit. This is essentially for trusses. We've looked at thermal stresses, and these were separate. Uniform for trusses. Why? Because you have to understand, uniform gives rise to axial, and differential for beams and frames. Why differential? Because differential is what gives rise to flexure. Okay? So, we have looked at all of these things for the analysis of statically indeterminate structures. After these lectures, we should be able to solve, using the force method, we should be able to analyze the forces and displacements in both trusses and beams and frames for external loading, for support flexibility, support settlement, lack of fit in a truss, and thermal stresses uniform in trusses and differential in beams and frames. So, this is what we should be able to do. Of course, you may say that, well, how do I solve a particular problem? You see, I am going to spend the next few lectures looking at a variety of problems so that you will be able to confidently use the force method to solve all these problems. The overall, over the last few lectures, what I have tried to do in essence is to lay out the theoretical basis. Okay? From here on out, I am going to be purely applying for example problems. Okay? So, this is the basic force method. Now, I am going to do a couple of problems over the next couple of lectures, and then we are going to move into the matrix approach for force method. See why matrix approach? Because if you see, essentially what you are trying to do is, if you are writing down, if you are writing down the equation, the compatibility equations becomes what? Something like x1l plus x1x is equal to 0. If you really look at this, this is more like, if I were to put it, it would be like a1 x1 plus a2 x2 equal to 0, and then you can put a3 x1 plus a4 x2 equal to 0. If you really look at this, this can be written in terms of a matrix as a1, a2, a3, a4 into x1, x2 is equal to 0, 0, if that is the thing. And this is nothing but a matrix. We can solve, what do we need to do? We need to solve for x1 and x2, and we can solve that using the matrix methods. That is not the only aspect of the matrix approach. The matrix approach not only uses matrix methods, but it also actually develops the entire procedure using a completely different theoretical premise. Okay? Of course, the basic concepts that we have looked at, how to compute deformation, how to compute, how to use the virtual force system, they all remain the same. It's just that they are set up in a different way. For trusses, you will see that they are really not very different. But for beams and frames, you will see that the entire basis becomes quite different. Okay? So, I just wanted you to introduce you today to this particular concept. So, just to lay out the next few lectures that I am going to be talking about, I am going to spend the next couple of lectures actually looking at some example problems. So, example, we will look at one truss, more rational truss. Up till now what we have been doing is we are looking at simple structures to essentially illustrate the method. You may say, well, all this is fine, but then when I look at actual truss, how do I solve that? We will look at that problem. We will take up a truss problem and incorporate as many things as possible into it so that you can gain confidence in solving the problems. Okay? And then I'm going to take up a beam problem. For an example beam problem, solve it all the way through. Then I'm going to take a frame problem, solve it all the way through. So that at the end of the next couple of lectures, you are ready to use the force method to solve any truss or beam frame problems totally by yourself. Okay? And then I'm going to move into the matrix method to introduce you to a different way of solving, and we will see quickly that the matrix method actually is a very, very good way of using the force method and very quick way of solving. But only thing is that it gets algorithmic and you lose sight of the basic. So that's the reason why I've used the force method to start off with in its basic form, so that you can look at the physics of the problem. Later on, the matrix method will make it an algorithmic way of analyzing structures. Thank you very much. I hope you've enjoyed listening to my lecture as much as I've enjoyed delivering it. Look forward to seeing you next time. Thank you. Bye.